All right, this is Mr. McMurray, and we're here with things that go bump in the lab. How exciting, huh? Uh, Sounds more Halloweenish, but it's a little late for that. Anyhow, so we're going to go, first of all, to our online textbook. So we will go www.essential-physics.com. All right, and when you do that, you should end up with something like this. Once there, you'll click on the state of Texas. Once you click on that, you'll stick on the word Texas. All right, once you get to the page here, you may have to put in the code, which is 742-098-4543. I'm sorry, I haven't turned off my computer since last time I did it, so mine came on up, but you may have to do this one more time. That number is 742-098-4543. Hurry now, and you may get free shipping. Oh, no, just kidding. Sorry, wrong thing there. All right, so anyhow, there we go. And you want to go to page 320 and then click go to page, and hopefully it will end up here, which is investigation 11B collision. So chapter 11, page 320. Now, there are two things that we said yesterday, part 1 and part 2. Today we're doing part 1, and this is a perfectly inelastic. All right. Now, once again, we said in real life, perfectly elastic and elastic collisions don't happen, but this is not real life. This is a simulation. So we can make it however we very well please. Okay. And this is how I please to do it at the moment. So that's what we're going to do. Now, let me look at the page, get where I can look at the page, and we will go over how to do this assignment. All right, now here's the worksheet. It says things that go bump in the lab. In your inline textbook, we did that. We're doing the one for inelastic collision. And the first thing it does, it says set the velocity of the green ball at 10 meters per second. So down here on the first one, you can hit clear over here if you like. Just be careful when it types in that it actually types in what you think it did. It really works better if you use the keyboard and the clear and enter buttons for that. Okay, so we have 10 meters per second. That's the first thing it said to do. Okay, now it says you want to experiment and figure out where both balls have the same velocity. Final velocity. Final velocity is going to be all right, so basically, I'm sorry, here we go. So where we go, well, both balls will have the same final velocity. Well, the question is, how do we do that? So we're going to have to experiment a little bit. And if we do experiment a little bit, let's say we do 5 and 5, and we run this. They're both the same size. Boom, there they go. Well, guess what? This is their mass afterwards, and here's their velocity. All right. And they do, in fact, have the same final velocity. Well, inelastic means they stick together. So guess what? No matter what you put on here, so let's put 20 and 20 just to do that and try it and see what happens. And boom. Okay. Since they stick together, guess what? They are always going to have the same final velocity. Okay. If they are the same size. Okay. That's the deal. All right. If they're the same size, then they're both going to stick together. They're going to have the same final velocity. And it's going to be halfway between what they started. The red ball was 0 and the other ball was 10 meters per second, so they're going to end up going, you have twice as much mass, so you're going to have half as much velocity because momentum is always conserved. Okay, now how do we need to fill out our chart? That's what we need to know here. All right, so if we do this, the mass, in this case, we made both of them 20, so we put 20 kilograms. I don't remember. Let me look real quick. Grams or kilograms? No, it's kilograms. Okay, so we're going with kilograms. All right, and we know that the other one we said was 20 kilograms. Whoops, whoa, something went wrong there. I don't know why that eraser pops up sometimes, but anyhow. Okay, 20 kilograms. All right, so that's the mass for both of them. Now, the momentum before, okay, would be formula for momentum, which is down here at the bottom, is mass times velocity. So it's going to be their mass times their initial velocity. This would be basically VI, okay, or initial velocity. All right, so VI. All right, and this would be the mass. The mass is not going to have initial and final because it doesn't change. Okay, so if you wanted to find the momentum before, you would just do 20 times 10, which gives you, I'm sorry, I didn't hear you. Ah, that's right, 200 kilograms times meters per second. All right. Okay, now if we did this one, 20 times 0 is going to give us 0 kilograms times meters per second. All right. All right, so there we go. Now, the velocity after, we're going to look at our thing, and it tells us that afterwards they were both going how fast? Well, it says 5 meters per second for that ball and 5 meters per second for the red ball. So this is green and this is red. Okay, and so we're going to go back. They're both going 5 meters per second. So we're going to type that into our document under the velocity after. That's going to be 5 meters per second. And the other one is also going to be 5 meters per second. All right. So that's good. Now the momentum after is going to be the mass times not the initial velocity, but now the final velocity. So this one right here would be, just for the record, VF. This is your final velocity. Okay. All right. And so the momentum after is going to be the mass, 20 times 5, which gives us 100 kilograms times meters per second. All right. And down here, we also have 20 kilograms times the final velocity, which is 5. So 20 times 5 is also 100 kilograms times meters per second. All right. Now, if we want to find the total momentum before, we would add these two together. So we could do 200 plus 0 gives us a total of, momentum before was 200 kilograms times meters per second. All right, and guess what? Lo and behold, if we add this one up, we get 100 plus 100, and we still have 200 kilograms times meters per second after the collision, which shows that momentum is conserved. Now, obviously, in real life, this might be a little bit lower because some of the energy and stuff is lost and so forth. But for this one, we're going to say, since it's perfectly inelastic, it will come out exactly the same. All right, now the change in velocity we know is VF minus VI. And so we know this is the final minus that, so it is going to be 5 minus 10 gives you what? A negative, that's right, 5 meters per second. All right, so it changed by that. This one changed by, you take the final, 5 minus 0, so it actually speeded up by 5 meters per second. Okay, so notice their velocities changed the same amount, but in opposite ways. Okay, this one decreased by 5 meters per second. This one increased by 5 meters per second. All right, and that's why the momentum before and after is still the same, because they both have the same mass before and after, and one decreased by 5 and one increased by 5, so the total velocity or total momentum being the same. Now, change in momentum is going to be the final momentum, if you prefer. Okay, the momentum after minus the momentum before. Okay, so the change in velocity for this one would be, you could do it 100 minus 200, which would give you a negative 200. The other option is what we've talked about before, which would be mass times delta V. Sorry, I can't make a delta here. Okay, mass times delta V, or change in velocity. So that would be the mass of 20 times the change in velocity, which is negative 5. So 20 times negative 5 is negative 100 kilograms times meters per second. Now, subtracting these two, the final minus that one, also gives you negative 100, and it's a good way to check and make sure that you got the right answer. Okay, here would be your mass times the change in velocity. So it had a change in momentum, change in momentum of 100 kilograms times meters per second. All right, and so once again, that's why the momentum before and after. This one lost 100 units of momentum. This one gained 100 units of momentum, making it the same. Okay, now you're going to do basically the same thing for the rest of the thing, but the next one is you want to mess with the different sizes or masses of the different balls and figure out what's the maximum final velocity for the balls to have at the end. Okay, and once you figure out which that is, you're going to put those masses in and then solve the problem again. All right, this one is where you want to get the minimum final velocity, the very least final velocity for the two balls. So how can you make them go as slow as possible at the end? Okay, so you're going to experiment around by changing the different masses of the ball, make one big, make one small, whatever, try things like that, try different combinations, and see which one will give you the lowest final velocity. Remember, the final velocity is what is over here, so you want to have the final. Now you're going to leave 10 here all the time, okay? You'll notice that's already been put in to all of your charts, okay? And so you're always going to leave the green ball as 10 meters per second and the red ball as 0. So the only thing you can change is changing the mass to try to make a maximum or minimum final velocity. Now, the last thing, you want both balls to have a final velocity of half of the green ball's initial velocity, okay? Which means the initial velocity is 10, that's right here, so that means you want the final velocity to be 5 meters per second. All right, so there you go, and that's what I'd like for you to do. There's one spare one down here at the bottom in case you mess up on one, but since you can just untype it, that probably shouldn't be a problem for you, but that's why it's here. So don't panic if you see this last one. What do I do with it? What do I do with it? It will be fine. All right, so you continue on, do the rest of it, and have a great day and a great weekend. Take the weekend off. You deserve it. I deserve it. Let's just all enjoy it. Have a good day.